Today we shall discuss the analytical solution of the series LCR circuit. Okay. Now see, whenever the three components L, C and R are joined in the circuit, then voltage across inductor, as you know, it is L di by dt. Then voltage across resistor is I into R. The voltage across capacitor is Q upon C. So if total voltage applied is V, then it is divided into three parts, VL, VR and VC, and if you add them, then total voltage V you will get. So V is equal to VL, VR and VC, they are added. So total voltage V is equal to L di by dt plus IR plus Q upon C. This is very clear. Voltage is divided, Kirchhoff rule also we can say. Now voltage which is applied is Vm sin omega t. So it is replaced by Vm sin omega t. Now see, as current I is dq by dt and di by dt is double derivative of charge. So instead of this di by dt it is written as d2q by dt square. And instead of this I it is written as dq by dt. So our equation will be like this. It will be L d2q by dt square plus R dq by dt plus q by C is equal to Vm sin omega t. Now see, it is divided by L. Okay. So just we have divided the whole equation by L. Okay. So this is a second order differential equation. Okay. Now see, the solution of this kind of equation can be Q is equal to Qm sin omega t plus pi, as we have studied all these things in 11th standard in the damped oscillator, wherever there were forced oscillation. Okay. So take the derivative of Q, then it becomes dq by dt is equal to Qm cos omega t plus theta, and the multiple of t is omega, so it is multiplied by omega also. Okay. So derivative is taken, then you take that another derivative. Okay. Then d2q by dt square will be, cos will have minus sign, so it becomes minus sin omega t plus theta, but this qm omega is already there, and multiply by the multiple of t is omega, so we have multiplied again by omega, so it has become omega square. Okay. Now these values are substituted, 3, 4, 5 are substituted in the equation number 2. Okay. Just we have to replace d2q by dt square by this particular value. Okay. Then dq by dt by this. Okay. And instead of this q we have to write qm sin omega t plus theta. That has been substituted here and it has been simplified. Barabar. And then the common is found. What is common? That is to be found. Okay. What is common? That is taken. Qm omega is common. See, here there is no omega, but we shall take omega as common and then we shall divide it by omega. Okay. So Qm omega is taken common, so inside it will remain minus L into omega sin omega t plus theta. Then R cos omega t plus theta it will remain. Here Qm has gone out, so it becomes 1 upon omega c sin omega t plus theta. Okay. The other side it is Vm sin omega t. Okay. Now see, again here slightly there is a change in the terms, order of the terms is changed. Here this RQM omega cos omega t plus phi, it is written here. Okay. It has been taken first, just change in the order has been taken. Okay. R cos omega t plus theta is taken first. Okay. Then this is taken plus 1 upon omega c sin omega t plus theta. Okay. Then this is taken minus L omega sin omega t plus theta is equal to Vm sin omega t. Now instead of this it is written xc, and instead of omega L we write xl. And sin omega t plus theta is common. You can see in this last two terms, what is common? Sin omega t plus theta is common. So it is taken common, sin omega t plus theta. Here it becomes xc and here it becomes xl. So it becomes xc minus xl. Okay. So this equation we got. Okay. Now we divide the whole by the term z. We are dividing it by z and multiplying also by z. So qm omega z, here it becomes r upon z, here it becomes xc minus xl upon z, here there is plus, so here also there will be plus, okay. Sin omega t plus theta is equal to Vm, z and z will be cancelled out, both the side it has been multiplied, that is why it is written, okay. So you can understand it very easily. Qm omega z, r upon z cos omega t plus theta, here it is plus, okay, here it should be plus xc minus xl upon z sin omega t plus theta. Now this r upon z is taken as cos phi, and this xc minus xl upon z is taken as sin phi, okay. It has been replaced by these two terms. R upon z is replaced by cos phi, and the other one, that is this, is replaced by sin phi. Here it will be plus, okay. So cos phi cos omega t plus theta sin phi sin omega t plus theta is equal to Vm sin omega t Qm omega z as it is, okay. Now you just find the ratio of sin upon cos will give you tan phi, which we have already discussed, or we have obtained this in the phasor method. That same equation we are getting, okay. So here our equation can be written as this cos omega t plus theta cos phi sin omega t plus theta sin phi is equal to Vm sin omega t. Here this remains as it is. Now this is the equation of cos omega t plus theta minus phi. It comes in the trigonometry, okay, and it can be written as cos omega t plus theta minus phi, okay. It is equal to Vm sin omega t. Now here taking theta minus phi is equal to minus pi by 2. This equation is also given, which is used here, okay. Cos alpha cos beta minus sin alpha sin beta is cos alpha minus beta, okay. So that equation we have utilized here. So here this becomes, and we are taking theta minus phi as minus pi by 2, okay. So this will be converted here as this equation, that is cos omega t plus minus pi by 2 is equal to Vm sin omega t. So this becomes sin omega t cos omega t minus pi by 2, or cos pi by 2 minus omega t is sin omega t. This is Vm sin omega t, okay. So now here Vm is nothing but Qm omega z. This you compare, Vm is Qm omega z. So here maximum voltage is Qm omega z, and Vm is equal to Im into z, okay. Vm is equal to what? Im into z. So here Im can be equal to Qm into omega. Just we are comparing. See, Vm is Qm omega z, so it is written as Qm omega z, and as you know that Vm must be equal to Im into z. It means that Qm into omega must be equal to Im, okay. Now current in the circuit, if you want to find, then just we have to take the differentiation. So I is equal to dq by dt. So just we have to take the differentiation of this Qm sin omega t plus theta, and that will give you Q. Already we have already obtained this Qm omega, so cos omega t plus theta. See, it is here only Qm cos omega t, Qm omega cos omega t plus theta. This is already dq by dt, which is nothing but current, that is again calculated, okay, here, okay. So it is Qm omega cos omega t plus theta. Qm omega is taken as maximum current, and maximum current is Im. So Im again Qm into omega. So I is equal to Im cos omega t plus theta, or I is equal to Im sin omega t plus phi, because theta minus phi is equal to pi by 2. So theta is phi minus pi by 2. So this can be written in this way. Im is equal to Vm upon Z. Z is known to you, that is modulus of Z. We are knowing value of impedance R square plus Xc minus XL the whole square. Okay, and phi is same results we are getting as we obtained in the other phasor method. Now the question is, what is resonance? A phenomena in which an external force or a vibrating system forces another system around it to vibrate with greater amplitude. You apply the force from outside, or something from outside makes the other system to vibrate at a greater amplitude, then this phenomenon of making the amplitude greater that of a particular system which is already vibrating, okay, that is called the resonance. A phenomenon in which an external force or a vibrating system forces another system around it to vibrate with greater amplitude at a specified frequency of operation is called resonance. Okay, now this phenomena is generally seen in the swing. When the child is swinging, the swing has a natural frequency for swinging back and forth. If the child pulls on the rope at regular interval and the frequency of the pull is almost the same that of the frequency of the swing, then the amplitude of the swing will become large, or the hichka mota thashe, a swing will have greater amplitude. Okay, and swing cannot stop. This is called the resonance. Okay, so whenever the child is swinging, then we have to either pull the rope, okay, pull the rope with the same frequency as that of the frequency of oscillation. If you are not pulling the rope at the frequency of the oscillation, then there may not be the increase in the amplitude. But if this applied force is having the same frequency as that of oscillation, then what will happen? The amplitude of the swing will increase gradually. Now explain resonance for the LCR circuit. Now to make resonance means to increase the current in the circuit, that's all. Current is given by our formula Vm upon Z. Okay, and Vm upon Z is the equation which is like this. Now try to understand, if you want to increase the current, then the denominator has to be minimized. Okay, here we know Xc is reactance of capacitor, that is 1 upon omega C, and XL is the reactance of inductor. So they are replaced by their values 1 upon omega C and 1 upon n omega L. Okay, so it becomes, our equation becomes Vm R square plus 1 upon omega C minus omega L the whole square. Okay, now if you want to maximize this current, then this bracket must be minimum, and therefore what will happen? 1 upon omega C minus omega L must be equal to 0. Okay, so what will happen? The current Im will become Vm upon under root of R square, that is Vm upon R, and that will be maximum current. Okay, and this phenomenon is called the resonance to make the current maximum in the circuit, and that is achieved when Xc is equal to XL, because 1 upon omega C minus 1 minus omega L is 0. It means Xc is equal to XL. So reactance of capacitor and reactance of inductor must be having the same value, then this phenomena is obtained. So we can say it is Xc is equal to XL, or 1 upon omega C is equal to omega L. Try to understand, this frequency at which this phenomenon occurs is known as resonant frequency, which is denoted by omega 0. So it is denoted by 1 upon omega 0 C is equal to omega 0 L, or we can say omega 0 square is equal to 1 upon LC, because omega 0 L is equal to 1 upon omega 0 c. So if you multiply these to omega 0, then it becomes omega 0 square is equal to 1 upon LC, or we can say omega 0 is equal to 1 upon under root LC. So this is the value of the resonant frequency. Okay. Now whenever the resonance occurs, then the current in the circuit becomes maximum. You can see the value of this omega upon omega 0 as such. Value of the applied frequency is omega 0 and the natural frequency is omega. If this ratio omega upon omega 0 is equal to 1, try to understand. Okay, the frequency of the circuit and the applied frequency, okay, if both are same, then the ratio becomes 1, and whenever the frequency are same, that is applied frequency and the natural frequency of the circuit, at that time the current becomes maximum, this becomes maximum, and this phenomenon is called the resonance. Okay. Now resonant circuit have a variety of applications. For example, in the tuning mechanism of a radio or TV, wherever there is a tuning, this frequency should match. The antenna of a radio accepts signals from many broadcasting stations. The signals picked up in the antenna acts as a source in the tuning circuit of the radio. So the circuit can be driven at many frequencies. So when you are tuning the radio, you are changing the value of inductor. Try to understand. We have the formula omega 0 is equal to 1 upon under root LC. So if you change L, then you are changing the value of the inductance in your radio set. So omega 0 of your circuit changes, and whenever this value of your radio set omega 0 is equal to the value of omega that is of the station, then you will be having the resonance and you will be able to listen the sound of a particular station. Okay, at that time current becomes maximum and the sound also becomes maximum in the circuit. Okay. Now the resonance phenomenon is exhibited by circuit only if L and C are present. There must be a presence of L and C. Without L or without C or any one of the is absent, you will not have the resonance. Only then do the voltage across L and C cancel out each other's effect and current Im is equal to Vm upon R is obtained. Okay, this means that we cannot have resonance by only R and L or R and C circuit. There must be L, C both present with the resistor. Okay. Now there is an equation of bandwidth. Okay. Now see, first of all, the graph which we have already seen, that of this resonance curve. Okay. See, this is your resonant frequency omega 0. So slightly away, that is say delta omega this side and delta omega this side. Okay, this particular gap is known as bandwidth. So this value which we are getting, that is either omega 0 plus delta omega and omega 0 minus delta omega s. This is called the bandwidth. Now whenever you are tuning the station, try to understand, you must have experienced that whenever the knob is rotated from a particular place, you will be able to listen the sound of a station and then it becomes maximum, and then again if you just rotate, then again it goes down. So this place from where you are able to listen that particular frequency of sound or particular station, and wherever you end that particular sound to be listened, okay, this particular gap is a bandwidth. Okay, and this we can understand this properly in this way. Okay, so whenever we talk about the bandwidth, try to understand this way. We have a graph. Okay, you are tuning the radio from this particular place, you are able to listen the sound, then they become maximum, then it becomes minimum. So this gap is delta omega, this is also delta omega, and this is your resonant frequency omega 0. This value is omega 0. So omega 0 plus delta omega and omega 0 minus delta omega, then you will be able to listen that particular station in this particular range. Okay, so this delta omega this side and delta omega this side, so twice the delta omega will become the bandwidth. Okay, this is to understand what is the meaning of bandwidth. Now see, when this omega 1 is omega 0 plus delta omega, its value is current is having its value I RMS upon root 2. Okay, hence amplitude of the current at omega 1 is Im is equal to Vm upon Z, and that is, as you know, Z is given by R square plus omega 0 L minus 1 upon omega 0 C whole square. So I am by root 2, that becomes IRMS rather. Okay, that is becoming, we have just divided by root 2 on both the side. Okay, and when there is a resonance, try to understand, whenever the resonance occurs, this part becomes 0. So it becomes Im maximum by root 2, IRMS it becomes, and then it becomes Vm R root 2 because this part has become 0. Okay, so what will happen? This R plus omega 1 L minus 1 upon omega 1 C whole square is equal to R root 2. Okay, so squaring on both the side, just we have taken the square. Okay, and we have simplified, you are getting 2R square is equal to omega 1 minus 1 upon omega 1 C whole square. Okay, and R is equal to, you are getting this value. Okay, now omega 1 is omega 0 plus delta omega, so just we have written, instead of omega 0 omega 1, we have written omega 1 plus delta omega. Okay, on both the side. Okay, then we have multiplied the bracket omega 0 L plus delta omega L, here also it has been multiplied. Okay, then omega 0 is taken common here, so omega 0 L 1 plus delta omega upon omega 0, here also omega 0 C is taken common, you can see. Okay, omega 0 C is taken common. Okay, now omega 0 L plus 1 omega 0 L into bracket 1 plus delta omega upon omega 0 minus omega 0 L, okay, upon 1 plus delta omega upon omega 0. Why it has been taken? Because omega 0 square is equal to L into C. So instead of C we can write omega 0 square upon L. Okay, so here instead of this C, it is taken as omega 0 square upon L. So if you write, as you know, that it is omega 0 square is equal to 1 upon LC rather. So C is equal to omega 0 square upon L. So instead of this C, it is written as omega 0 square upon L. So what will happen? Instead of this C, if you write omega 0 square upon L, then that L will go in the numerator. Okay, again I am explaining. See, omega 0 square is equal to 1 upon LC. So C will be equal to 1 upon omega 0 square into L. So instead of this C, if you write this, okay, then here instead of this C, if you write 1 upon omega 0 square into L, then this omega 0 will be cancelled out and this omega 0 and L will go in the numerator. That is why here we have obtained omega 0 L. Okay, so it is clear now that why this omega 0 L has come here. Instead of this C we are placing the value. Okay, why C is equal to, as you know, 1 upon omega 0 square into L. So instead of this C we have to write this value. Okay, so that omega 0 L will come, and that omega 0 L can be taken as common. Okay, so very easy to understand now. Omega 0 L is taken common, and this 1 plus delta omega upon omega 0 is taken in the numerator. That is why its raised to minus 1 has become. Okay, and it has been simplified as 1. Okay, it is binomial expansion only. Just this step is as it is. Instead of this 1 plus delta, this is equal to r. Okay, it has been removed. Okay, so this is equal to r. Okay, so instead of this particular bracket, it has been written as 1 minus delta omega upon omega 0. That is binomial expansion. You can directly write, no need to show this. Okay, that is equal to r. Okay, so it is taken common, and that is equal to r. Okay, again this is equal to r, this is equal to r. Okay, so here 1 will be cancelled out. Okay, omega 0 L, this becomes twice delta omega upon omega 0 is equal to r. So delta omega is equal to r upon 2L, that we are getting. Okay, now continuation of that, what is sharpness of resonance? Now see, this sharpness of resonance is defined as omega 0 upon 2 delta omega. Okay, so instead of this delta omega, what we got, r upon 2L. Delta omega just now we got, that is r upon 2L. Now if you substitute instead of this delta omega r upon 2L, then you will get this equation, that is omega 0 L upon r you will get. Here omega 0 upon L, omega 0 L upon r is called the quality factor, which is defined as omega 0 L upon r. Okay, so omega 0 L upon r is a quality factor. Okay, so here Q, that is resonance frequency upon bandwidth, quality factor is also defined in this way. Omega 0 upon 2 delta omega, that is resonance frequency upon bandwidth, that is omega 0 upon omega 2 minus omega 1. Okay, so 2 delta omega, that is bandwidth, is omega 0 upon Q. Okay, so here we know that omega 0 square is equal to L into 1 upon L into C. In Q is equal to omega, so Q is given omega 0, or rather we have obtained Q is equal to omega 0 L upon R. Now instead of this omega 0 square, we write 1 upon LC, or we write say L is equal to 1 upon omega 0 square C. Okay, so what will happen? Instead of L we write this value. Okay, so we will have omega 0 upon R multiplied by 1 upon omega 0 square C. So omega 0 will be cancelled out. Okay, you will have 1 upon omega 0 R into C. Okay, this value you will get 1 upon omega 0 R into C. Okay, if you have all the three components, okay, as you know that Q factor is nothing but omega 0 L upon R. This value you have to remember, omega 0 L upon R. Omega 0 L upon R is the Q factor. Okay, now if you have this, say for example omega 0 is 1 upon LC. So omega 0 square is, rather I can write it the different way. Okay, omega 0 is equal to 1 upon under root LC. So if you place this value here instead of this omega 0, then Q is equal to 1 upon under root LC multiply by L upon R. So it will become 1 upon R under root, because this root will go this side, under root L upon C. Okay, so that value is obtained at the end. Okay, for LCR circuit you can just replace these values and you can get the answer in any terms, L, C or R. Okay, for parallel circuit, Q factor is defined as VL upon R or VC upon R. Okay, if the resonance is less sharp, not only is the maximum current less, the circuit is close to resonance for a large range delta omega of frequencies, and the tuning of the circuit will not be good. Try to understand. If this kind of graph is there, then there is a sharp tuning. At a particular frequency you are having a tuning. But if you have the graph like this, then there is no sharp tuning. Okay, and the bandwidth is very high, so you do not have a proper resonance with the external circuit, or tuning will not be proper. Okay, thank you very much.